Okay, great. So welcome to this month YRQG seminar. Today's speaker is Leonardo de Gioia, and Leonardo did his master studies at the University of Campinas and graduated there in 2019. Since then, he is a PhD student under supervision of João Paulo Pitelli, and he will actually finish his PhD still this month. Leonardo's research focuses on celestial holography and related topics, but he's also interested in quantum gravity in general and in string theory in particular. Today, he will give us an introduction to celestial holography and its relation to the flat space limit of AdS CFT. So thanks a lot for accepting our invitation and being here today. And whenever you're ready, please feel free to start.
Thanks, Tobias, for the introduction. Thanks also to the organizer for the invitation. Let me share my screen here. So I'm going to talk about an introduction to celestial holography and a connection to the flat space limit of AdS CFT. In particular, this last part about connecting to AdS CFT is the subject of my work, and it's based on these two papers here with Ana Claudio. So here is a brief overview of what I plan to talk. And basically, I'm going to start reviewing celestial holography, and then I'll start talking about the motivation for this flat space limit of AdS CFT, and finally how it suggests the connection between celestial holography, celestial CFT in general, and a dimensional reduction of standard conformal field theories. So first, I want to start introducing celestial holography, and let me start with the motivation. And basically, the motivation is to apply the holographic principle to asymptotically flat spacetimes. So the holographic principle is this general principle that a quantum theory of gravity should be equivalently described by a non-gravitational theory in lower dimensions. And it's motivated in part by the black hole entropy, which is proportional to its area instead of the volume. And while this is a general description of what the holographic principle is, we need to formulate it precisely in a case-by-case basis. And in particular, in asymptotically AdS spacetimes, it admits a very precise formulation in terms of the AdS CFT correspondence. So one example of this duality, the AdS CFT duality, is given by Maldaceni's conjecture, which basically is the statement that type 2B superstring theory in AdS 5 cross S5 is dual to n equals 4 supersymmetric Yang-Mills theory in the conformal boundary under certain identification of the couplings between the two theories in the two sides of the duality. So this is just one example which started this whole AdS CFT correspondence. However, there are many other examples, and it's believed that in general, quantum gravity in AdS should be dual to a conformal field theory that lives in the boundary of AdS. So this is particular to asymptotically AdS spacetimes, and the extension to more general spacetimes such as the real world is an open problem. Well, in particular, one possible extension would be to asymptotically flat spacetimes, which approximate several situations in the real world that are of interest. And in particular, this is basically the Penrose diagram of Minkowski space. And the idea of an asymptotically flat spacetime is that it may be very different from Minkowski deep in the bulk, but as one goes to large distances, it becomes like Minkowski. So basically, it has the same asymptotic structure of Minkowski spacetime. So in this diagram here, deep in the bulk, this spacetime can be very different, but it will have the same boundary structure as Minkowski space. In particular, its boundary is more complicated than that of AdS, which is a time, in the AdS case, we have a time-like boundary, but here we have actually these null surfaces, which are future and past null infinities, scry plus and scry minus. And that's in part what makes a flat holography different than AdS holography. And basically these null surfaces, scri plus and scri minus, they have the topology of a null line cross a sphere cross S2. And this sphere at null infinity is what we call the celestial sphere. So the idea of celestial holography is that a quantum theory of gravity in an asymptotically flat spacetime should be dual to a two-dimensional theory that lives in the celestial sphere at null infinity. So it's a bit different than AdS CFT because the dual theory lives in 2 dimensions less than the boundary theory instead of in just 1 dimension less than the boundary theory. And we call this theory in the celestial sphere a celestial conformal field theory because it shares several properties with conformal field theories, but it also has some unique features, as I'm going to review. And the motivation for celestial holography is the connection between soft theorems and asymptotic symmetries that has been discovered in the last decade. So the idea of studying these asymptotic symmetries is that whatever the holographic duality in asymptotically flat spacetimes should be, the symmetries between the two theories, they should match. So in particular, an asymptotic symmetry is a gauge transformation that respects the boundary conditions that are imposed in the theory, but has non-trivial action at infinity. So as one approaches that boundary, one has a non-trivial action. In particular, given this definition of an asymptotic symmetry, one defines the asymptotic symmetry group to be the quotient between the allowed gauge transformations, meaning those that preserve the boundary conditions, and the trivial ones, which are those that die off at infinity. So there is a whole literature on the study of asymptotic symmetries and of these asymptotic symmetry groups. And in particular, in the case of gravity in asymptotically flat spacetimes, asymptotic symmetries have been studied, for example, by Bondi, Vanderburg, Messner, and Sachs in the 60s. And they found, by carrying out this analysis of asymptotic symmetries, they found what's now called the BMS group. So they have found Lorentz transformations as would be expected, but instead of just finding the usual translations that we have in Minkowski space, they have found one infinite dimensional enhancement of translations that are called super translations. So to describe what those symmetries do near the boundary, in the case of super translations, they act on the generators. They act on scribe plus and scribe minus. Here I have scribe plus by shifting along the node generators in an angle dependent way. So basically they shift each point in these spheres, in these cross-sectional spheres differently depending on the angle. So that's what they do. On these, they enhance the usual 4 translations because the 4 translations, they are particular super translations, but we have here extra one. There's an infinite dimensional enhancement. On the other hand, Lorentz transformations, they're the usual transformations that we know from Minkowski space. But when we studied Lorentz transformations at infinity, we find that they act on these celestial spheres as global conformal transformations. So the action that Lorentz transformations perform on the spheres at infinity, they are just the global conformal transformations of these spheres. And it has been proposed by Bonich and Tresai some time ago to generalize these Lorentz transformations to transformations that are called super rotations, which means that we enlarge the global conformal algebra of these spheres to the full local conformal algebra. Now, when this is done, the boundary conditions that BMS studied are violated at the singular points of the vector fields. However, there is justification for this enhancement that comes from soft theorems, as I'm going to review in a bit. So, once we have these symmetries, we can study the charges that generate these symmetries in phase space in the classical theory or in the Hilbert space in the quantum theory. And in particular, in a canonical formulation, we can find charges that are defined at the boundaries of scribe plus and scribe minus. These are surface charges. They are integrals over a codimension 2 surface in space, in the boundary of space-time. And basically, there is a whole algorithm to compute these charges that is known as the covariant phase space formalism. But the important point is that these charges in the classical theory, they are conserved and they're a suitable antipodal identification of the boundaries of spri plus and spri minus. But what's relevant, and here is where lies the connection to soft theorems, is that these charges, one can study their word identities in the quantum theory, in the sense that we study basically the commutator of the charges with the S matrix. So the symmetry statement in the quantum scattering problem is that these charges commute with the S matrix, and we have expressions for these charges, and we can expand these out and study these conditions in detail. And what we find when we do that is that these charges, they admit a soft hard decomposition, by which I mean that they have one part which is linear in the gravitational field, which is called the soft part, and a part which is quadratic in the gravitational field and depends also on the matter field, is called the hard part. And what's important is that this soft part, it contains creation and annihilation operators of gravitons with energy taken to zero. So it involves limits of graviton operators as we take their energies to zero. So these are soft insertions. So to establish these asymptotic symmetry word identities, what we need to do is to study the behavior of the S matrix when we insert additional gravitons and take their energy to zero. And in fact, this has been studied also in the 60s. The first studies were in the 60s by Weinberg, for example, and some other people in the context of QED, but in the gravitational case by Weinberg. And these soft insertions, they are given by the so-called soft theorems. So basically, when we insert a graviton in the outgoing state with energy omega, it turns out that we have a factorization in which we get one expansion in the energy times the S matrix without that graviton. So these expansion in the energy, it starts with a pole, and this first term here is called the leading soft term, the leading soft factor, and it has been found by Weinberg. It takes this form. And the subleading term has been found just more recently by Kachaza and Strominger, and it takes this other form here. Here, these few hat vectors, they are null vectors in space-time that capture the direction of the particle. So they're basically embeddings of the sphere on the light cone. And these epsilons here, they are the polarization tensors of the gravitons, while these J's, they are the Lorentz generators acting on the K particle in the S matrix. So the subleading, for example, the subleading soft factor is actually an operator acting on these S matrix here, while the leading soft factor is really just a number. There is also a subleading soft factor here that has also been found by Kachaza and Strominger. Now there is evidence that this expansion actually continues down to further subleading orders. Now, given these results here, these soft theorems that can be proven by standard quantum field theory methods, one can go back to those word identities and compute them exactly, and start with the soft part of the charges and check that the hard part is reproduced. So starting from these expressions of the soft theorems, it is possible to prove that the asymptotic symmetries word identities hold true. So in particular, soft theorems, they imply an asymptotic symmetries of the scattering problem. Well, of course, this depends on the validity of the soft theorems, and there is one remark that I want to make, that the leading soft graviton theorem does not receive quantum corrections. However, the subleading soft theorem does receive quantum corrections. In particular, it has a one-loop exact infrared divergent contribution to that soft factor. But it has been shown that these one-loop exact infrared divergence can be eliminated by a renormalization of the generator, so the symmetry survives at quantum level. And there's just some subtleties here, because it could be the case that in some cases there could be some finite corrections as well to that subleading soft theorem. However, this is not I mean, in the examples that have been studied so far, these finite corrections, they do not appear, they are zero. So there is good evidence that superrotation symmetry also survives at quantum level. So these remarks, they are to say that these symmetries, they are implied by the soft theorems, and it's believed that they are actual exact symmetries of the S matrix. Now, why this has anything to do with flat space holography? And the answer is the following, is that for certain parameters of the supertranslation and the superrotation, so for particular supertranslations and superrotations, these symmetry statements, those word identities, they take the form which is characteristic of symmetry statements in a two-dimensional conformal field theory. So in particular, if we define this PZ to be basically the soft part of the supertranslation charge for this particular supertranslation here, where ZZ bar is one fixed point on the sphere, it turns out that insertions of this PZ here, this is the supertranslation word identity for this particular supertranslation. So basically, insertion of this PZ here take this form, which is basically the form of a U1 Katz-Moody word identity on the sphere, where the operators are placed at the various points on the sphere at which the particles enter or exit space-time, and where the charges are the energies. And likewise, if we define this TZZ here to be the soft superrotation charge for this particular superrotation vector field, it turns out that the superrotation word identity takes exactly this form here, which is basically the form of a two-dimensional conformal field theory stress tensor word identity, where again the operators are placed at the various positions at which particles enter or exit space-time on the celestial sphere. These HKs here, they are what would be the conformal weights, and it turns out that they are actually operators. So they are basically these operators here. So they are given by this form, where Sk are the spins of the various particles that we're scattering, and where this quantity here, omega d by d omega, this plays the role of the conformal dimensions. So it turns out that the S matrix, it behaves in many ways as a conformal correlator on the celestial sphere. However, it turns out that the operators seem to have these non-standard conformal dimensions, which are operator value. So this motivates one to diagonalize these dimensions, diagonalize these operators here. And that, in fact, ends up being the starting point of celestial holography, because we can find a set of states that diagonalize these operators here, and it's very simple. We just take this Snelling, in the massless case, it's very simple. We just take this Snelling transform here of the standard energy momentum eigenstates, and this Snelling transform exchanges the energies of the particles by these conformal dimensions. So this is at the level of states, and at the level of wave functions, we map the plane waves, which are momentum eigenstates, to these functions here, which are called conformal primary wave functions. So these conformal primary wave functions are labeled by a point on the celestial sphere, which indicates the direction at which the particle is moving, is the direction of the momentum. And we also have this conformal dimension here, which can also be interpreted from the bulk perspective as a boost weight. This is for scalars, and for spinning particles, we need to dress with polarization vector tensors or spinors here. This is the story for massless particles. In fact, I'm only talking about massless particles here. There is a different story for massive particles, but I'm not going to discuss that in this talk. Now, the idea of celestial holography then is that the S matrix, when written in this basis, it behaves in many ways as a conformal correlator. In particular, it obeys a stress tensor word identity, where now the operators are placed at the various positions at which particles enter or exit spacetime. And now they have standard numeric dimensions. They don't have anymore these operator value dimensions. So the basic idea is that the S matrix elements in this conformal primary basis, they are what we call celestial amplitudes or celestial correlators. And what's the idea of celestial holography is that we interpret these celestial amplitudes as actual conformal correlators on the sphere, as conformal correlators of a two-dimensional theory defined on the celestial sphere. And then we can study several properties of these conformal correlators. One comment here is that up to this point, most of the analyses have been in a bottom-up approach in which the bulk defines whatever is in the boundary. So these conformal correlators on the sphere, these celestial amplitudes, they are actually defined to be Mellin transforms of the standard S matrix, going from the standard energy momentum basis to a conformal primary basis. So in fact, the connection to AdS CFT is in part motivated to try to give one intrinsic construction of a celestial CFT without resorting to the bulk in the first place. So, well, here's a very short list of some celestial CFT results. So one results that conformally solved theorems have been established. So when we go to the conformal primary basis, we exchange the energy for a conformal dimension, and then it's not clear how these soft theorems translate into that basis, since they are statements about the low energy behavior of some insertions. However, it turns out that it's possible to translate them in the so-called conformally solved theorems, and that's one point I'm going to give some more details. Also, there has been studies of IR and UV properties of 4-point celestial amplitudes, and also a prescription to define one infrared finite S matrix. One operator product expansion in celestial CFT has been shown also to arise from collinear singularities in the bulk, and that's another point I'm going to give some more information on. These OPEs have also been found to be fixed by symmetry arguments. These OPEs have been used to understand the so-called holographic symmetry algebras and to understand the W1 plus infinity symmetry of gravity. And this W infinity symmetry of gravity has also been shown to be realized in the Einstein equations of classical general relativity ad null infinity, providing one check of these ideas. So this is just one very short list of some results. There are many others. In particular, there are some very interesting connections to twistor theory and some other stuff. That's one very short list, but some very important results. Now I'm going to just go through a bit of some features of celestial holography, and then I'll go talk about the flat space limit of AdS CFT. So, for example, one thing that can be studied in celestial CFT are the Poincare constraints. This is the most basic symmetry that we have in the bulk. And in particular, the Lorentz group, as I have already said, it acts on the celestial sphere as the global conformal group by global conformal transformations. And as a result, Lorentz constraints on celestial amplitudes, they translate into the well-known global conformal constraints on correlation functions of a two-dimensional conformal field theory. So that's the standard. That's the standard standard symmetry from a CFT perspective. Translations on the bulk, on the other hand, they are additional charges that will act on these celestial operators, and they are not there in a generic one standard conformal field theory. And what they do, translations, they basically, the non-trivial thing they do is that they shift the dimensions of these celestial operators. So they act as weight shifting operators on these celestial operators, and this imposes additional constraints on celestial amplitudes on top of the standard conformal constraints. In particular, one example of such constraints is this one, that when we shift each of the dimensions of a conformal correlator, of a celestial correlator, and sum all of them up, we should get zero. This is one constraint that's non-trivial and it's not there in the standard conformal field theory. And moreover, translations constraint also imply that 2, 3, and 4-point functions of a celestial CFT, they have singular dependence on the points on the sphere, which is also a non-standard feature of celestial CFT. One particular case in which these constraints, well, we can see how different what they imply in difference to standard conformal field theory is in the case of the 4-point function. And in the case of the 4-point function, the celestial 4-point function takes this form where this k here is a conformally covariant prefactor, where these z and z bar, they are the conformal cross ratios here. They are conformal invariants built from these 4 points, z1, z2, z3, and z4. And this beta here is the sum of the dimensions. So in a standard conformal field theory, we would have the conformally covariant prefactor here. That's the standard part. And then we would have a function of the cross ratios. The non-standard and unusual features that we find here is that we have this singular dependence on the cross ratios by this delta function. And we also have this dependence on the dimensions that occur only through their sum. So these are some unusual features, and they are a result of bulk translations. The conformally soft theorems, well, here I am just giving some more details of what happens with that. And the basic idea is that the standard soft theorems, they have to do with limits as the energy of a particle goes to 0 inside correlation functions, sorry, inside of asymmetrics elements. And it turns out that because of this delta function identity here, when we take the Mellin transform, it's possible to translate the soft theorems, the omega go to 0 limits, into limits in which the dimensions go to particular values, which are these values 1 minus s, where s is greater or equal to 0. So we have negative dimensions here, and operators at these negative dimensions, they basically capture exactly the soft theorems to various subleading orders. And so in particular, these facts here imply that these conformally soft operators, when we insert them into these celestial correlators, they obey a factorization, which is similar to the standard soft factorization, where now we have this conformally soft factor. And finally, well, the last thing that I want to talk about celestial CFT in general before going to the flat space limit of AdS is the celestial OPE. And so basically, scattering amplitudes in a plane wave basis, they have singularities when two particles become collinear. So this for massless particles. And these singularities, they basically, they are singularities of the form 1 over z12 and z bar 12. So they are singularities that translate to coincidence limit singularities in the celestial sphere. And scattering amplitudes are known to factorize in this limit. And it turns out that when we take the Mellin transform of this factorization, we find something that resembles one standard OPE. In particular, these G's here, they are graviton operators. And we have these OPs here, they can be derived by taking the Mellin transform of these collinear singularities. And these OP can also be constructed from symmetry arguments. In particular, this OP is a very important tool that has led to the realization that gravity enjoys this W1 plus infinity symmetry. And the basic tool in doing so, I'm just skimming through it's just one schematic idea of what happens, is that we take a transform called the light transform of these gravitons, and then we take the dimensions to approach the conformally soft values. And when we do that, apart from a divergent piece that we can subtract, we get some operators on the sphere which encodes currents which obey the so-called W infinity algebra. So what is actually going on here is that these soft symmetries that we started talking about, which were the super translation and super rotation symmetries, we get several others that come from the further subleading soft theorems, and they reorganize into these algebra. So these are basic some results of celestial CFT. And as I said, there are many others. Now, now I'm going to talk about this flat space limit of AdS CFT. And the motivation to study that is that contrary to standard AdS CFT holography, in which we have several dual pairs that we can construct from string theories, in celestial holography, we do not have a general framework to construct dual pairs. And in particular, one very important open question is how to intrinsically define a celestial CFT and how to construct these dual pairs. In particular, very recently appeared a construction in self-dual gravity. So in self-dual gravity, now we have one particular construction of that. We have one proposal of a dual pair, but it would be nice to have one general framework to construct such dual pairs. And in particular, one way to do that is to connect to AdS CFT. That's the proposal. So geometrically, what happens is that it's known that we can take one limit in which the AdS space becomes Minkowski space. In particular, this is the AdS metric in global coordinates. And what we do is that we make a redefinition of coordinates by rescaling by the AdS radius, and we take a large radius limit. And when we do that, we get the Minkowski metric. So geometrically, as I'm going to show in a picture soon, what we're doing is that we are zooming into a region near the center of AdS that turns flat as the AdS radius is large. So there are several studies to connect conformal correlators in AdS CFT to the S matrix in Minkowski space. And more recently, one such proposal was that conformal correlators with operators near global times plus or minus pi over 2 in the AdS boundary should give rise to the S matrix in momentum basis after we take some integral transforms. So motivated by that, we take this flat space limit configuration in which we basically redefine the coordinates in the bulk and to take that flat space limit. And in the boundary, we expand about plus or minus pi over 2. And so we take this limit of large AdS radius. In particular, here is the geometry of what's going on. And basically, this here is AdS. This for the picture is for a shockwave flat space limit, but it's just to illustrate the point. Basically, this is AdS, and this small region here, this small diamond, is what turns into the flat Minkowski space as we take the large AdS radius. And basically, the minus pi over 2 and pi over 2, they are the relevant points on the boundary, because light rays coming from minus pi over 2 will go through the center and reach pi over 2. So that's the basic idea of this flat space limit. And as I said, while there are some studies on the flat space limit of AdS CFT in order to construct the momentum space S matrix, the S matrix in the basis of momentum eigenstates, we would like to directly construct the celestial amplitudes, the celestial correlators, and therefore relate celestial CFT to standard CFT. And a way to do that is by recalling that in perturbation theory, the dual CFT correlation functions are calculated by means of AdS Witten diagrams. So this is one example of a Witten diagram, one tree-level exchange diagram. And the basic idea is that these Witten diagrams, they are made of basically three constituents, which are external lines, which are the bulk to boundary propagators, internal lines, which are bulk to bulk propagators, and vertices, which are basically integrals over AdS. And our strategy is then to expand the individual components of large AdS radius. And when we do that, basically the bulk to boundary propagators, when we expand them by setting the operators at plus or minus pi over 2, is that we find that they reduce to the conformal primary wave functions. That's the main aspect of this proposal. So it's necessary to make one antipodal identification of the two slices, because we need to place operators at pi over 2 at some point, and then at minus pi over 2 at the antipodal point. So that's a technical detail of this calculation in order to get the correct conformal primary wave functions. But we get these conformal primary waves as we expand the bulk to boundary propagators in the flat space limit. The bulk-to-bulk propagators, they can be studied by looking at the equation they obey. And if we just take the defining equation of the bulk-to-bulk propagators and expand the equation at large AdS radius, we find that the Laplace operator becomes the standard flat space wave operator. This delta function becomes the standard flat space delta function. And we get the equation for the, at leading order in the larger expansion, we get the equation for the Feynman propagator. The mass of the exchange is then related to whether we scale this dimension, this intermediate dimension, with the AdS radius or not. So we can get either massive or massless exchange. So the bulk-to-bulk propagators, they become the standard Feynman propagators as we take the AdS radius to infinity. And vertices, they are integrals over AdS, and we can expand those integrals. And when we do that, we recover flat space integrals. So the basic, the components of an AdS Witten diagram, as we take the AdS radius to infinity in that flat space limit configuration, they reduce to the corresponding Feynman diagrams elements computing celestial amplitudes. And the reason for that is that we get the position space Feynman rules for S matrix elements in which the external states are the conformal primary wave functions. Because basically the external lines, they are not the plane waves, but rather the conformal primary wave functions. All of that, of course, provided that there are no subtleties in expanding those integrals, and that's something that is still being studied. We're still studying that. But the important point is that we have evidence that correlation functions of a holographic CFT, when operators are placed at plus or minus pi/2, reduce to celestial amplitudes when we take this flat space limit of AdS CFT. In particular, this can be checked explicitly in a shockwave. So that picture was of a shockwave in AdS, and we can compute a two-point function in the shockwave background. And then we have one explicit non-perturbative check of this connection here, because that the shockwave two-point function is non-perturbative. And so in particular, what this suggests is that celestial CFT may arise as a dimensional reduction, as a species of dimensional reduction of a standard conformal field theory. And I want to remark on two generalizations. The first is that these arguments that I have given, they are for scalar operators, but they can be generalized. And so we can also recover spin-in celestial amplitudes and spin-in exchanges as well from this flat space limit of AdS Witten diagrams. And while we have in this argument placed the operators exactly at plus or minus pi/2 in the AdS boundary, we can more generally place them at a small infinitesimal 1/r displacement of plus or minus pi/2. When we do that, this additional variable u can be traded by a shift in conformal dimension by one integral transform, but it can also be suggested by symmetry arguments. So I'm not going to show it right now. Let me just see how long. So, well, and then the idea is that we can, motivated by that, study the symmetries of celestial CFT in the sense of trying to understand how they emerge from this dimensional reduction procedure, how they emerge from standard conformal field theory on these, when we basically localize to the neighborhood of some time slice in the boundary. So the basic idea is that conformal transformations, they are generated by conformal Killing vectors, which are vector fields obeying these equation here, and we can study this equation on the cylinder in the neighborhood of some time slice. And basically, when we do that, we find, since we have this parameter to expand this R parameter here, find a family of vector fields that are parameterized by a function on the sphere and a conformal Killing vector on the sphere, pretty much like BMS transformations, which are these vector fields here. And it turns out that we can before that, it turns out that these vector fields, they obey almost of all of the conformal Killian equations. So except one of them, in which we have these 1/r terms on the right-hand side, the conformal Killian equation demands this to be 0. And it turns out that if we want to solve the equation for finite r, so away from this limit, we need that this function be constant and that this conformal Killian vector on the sphere be actually globally defined. So these are the standard, then we recover the standard conformal transformations of the cylinder. However, if we take R to infinity, the equations are satisfied and we get an infinite dimensional enhancement. It turns out that it's possible to reorganize these vector fields in such a way that we basically take these linear combinations of them, and these Ly's and TF vector fields here that we get, they obey exactly the BMS for algebra. Actually the extended BMS for algebra, because these Y's, they are the superrotations, they are actually locally defined conformal Killian vectors on the sphere. So basically the claim is that what we have found is that if we just study conformal symmetry of the cylinder in this limit as we expand about a time slice, we find a set of vector fields parameterized by a function on the sphere and a conformal Killian vector on the sphere that obeys the BMS, the extended BMS algebra. This is the algebra that one finds in flat space. And it's rather remarkable that this algebra that is found by studying asymptotic symmetries in asymptotically flat spacetimes emerges the conformal symmetry of the Lorentzian cylinder on a small neighborhood of a time slice. In particular, we know that a primary operator in conformal field theory transforms in this way conformal. And in particular, we can study how conformal primary operators transform under these extended symmetries that we have found.
Leonardo,
and when we do that,
sorry to interrupt you, but we have a bit of connection problems. Maybe you can turn your camera off or some.
Okay.
Just for the moment to stabilize the connection maybe a bit. Thanks.
Okay. By the way, how long do I have yet?
I would say 10. I would say 10 minutes.
10 minutes. Okay, that's. So a three-dimensional primary operator, as I said, it transforms in this way under conformal maps, infinitesimal conformal maps, and we can study this transformation law for these vector fields Ly that generate what we think to be superrotations. And in particular, that's interesting because what the time slice, so we will then be studying how operators transform when they're restricted to these time slices. And when we do that, the claim is that if we take these superrotation vector fields here on the cylinder and study the transformation law of a conformal primary operator in CFT3, we get exactly the transformation law of a two-dimensional primary operator on the sphere, except that its conformal weights, they are operator valued, pretty much like what happened when we studied the S matrix in asymptotically flat spacetimes in the standard plane wave basis. Here, the geometry of this statement is basically that what's going on is that a three-dimensional primary, when just restricted to a time slice, does not transform as a two-dimensional primary. Rather, it has this operator value mentioned here. And J3 here, it's basically the angular momentum along the three direction. And well, the three-dimensional primary is J3, so we just get the spin. But these dimensions, they are actually operator value. And only when we set the operators exactly at plus or minus pi/2, we really get something that diagonalizes the two-dimensional conformal transformations. So saying this differently, what happens is that if this capital D here is the three-dimensional dilatation generator, and this script D is the two-dimensional dilatation operator, the three-dimensional primaries diagonalize this D here on the origin, but they don't diagonalize the two-dimensional one on the origin of when we place them on the origin on the sphere. Rather, we get this extra operatorial term. However, we can, as one does in flat space, we can diagonalize that, and that's done by a time Mellin-like transform. It's not exactly the Mellin transform, something a bit different, but we can do that. And these modes here that we extract from the operator, they now transform exactly as two-dimensional primary operators with these dimensions here. So the idea, a summary of this, is that we can find transformations on the cylinder that they impart two-dimensional conformal transformations on the time slices, and we can then extract from any three-dimensional primary a continuum of two-dimensional primaries that transform as two-dimensional primaries would under these transformations. And in particular, this is the transform that I said at the level of written diagrams that can be introduced to deal with that small coordinate about plus or minus pi/2. And this is just normalization that can be chosen for convenience. And all of this generalizes to conformal field theories in any number of dimensions, and celestial conformal field theories in one dimension less. So here is one very quick comparison with standard Kaluza-Klein reduction. So in Kaluza-Klein reduction, we have a field in this product space, which is Rd cross some compact K. And we have the mass Casimir on the higher dimensional space, the mass Casimir on the lower dimensional space, this Rd. And the field diagonalizes the mass Casimir on the higher dimensional space. But when we study the action of the lower dimensional mass Casimir, we rather get an operator here. We don't really get, it doesn't diagonalize that. But we can diagonalize the lower dimensional mass Casimir by integrating over this compact K. And when we do so, we introduce this tower of fields of several masses. In our case, we have a field in the cylinder, and we have basically that it diagonalizes on the origin on the higher dimensional space, but on the lower dimensional space, it doesn't. And we can diagonalize that in the same way by integrating over now, we integrate over R instead of over a compact space. In particular, since here we have a compact space, in general, we get here a discrete tower of fields, and here we instead get a continuum of fields because R is non-compact. So what we have really is a dimensional reduction of a conformal field theory. That's really what we are actually constructing here. So these are just the remarks that I just made. In particular, one particular case is that we can take that parameter of the transform, that lambda, we can take to 1, and when we do that, the limit is singular. And nevertheless, we can extract a residue, and when we do that, we recover operators exactly at u equals to 0. So again, we recover that prescription of placing operators exactly at minus pi/2. So that's one special case of this diagonalization of the two-dimensional dimensions. So finally, and that's the last part, I mean, we can then ask about the soft symmetries. So a key signature of celestial CFT are the soft symmetries, and we could try to find out if they emerge in this dimensional reduction. And in particular, it's non-trivial that they do so because it's non-trivial that a standard three-dimensional or higher dimensional conformal field theory can have this large amount of symmetry that a celestial CFT has because of soft theorems. So the answer to this question is that they do emerge from this dimensional reduction procedure. And the way to use that is basically to recall that the leading and subleading conformally soft modes, they have dimensions equal to 1 and 0. The stress tensor in a conformal field theory has dimension d, while a current has dimension d-1. And there is a transform that's called the shadow transform that maps an operator of dimension delta to an operator of dimension d minus delta. So in particular, it maps the stress tensor to a dimension 0 operator, and it maps the current to a dimension 1 operator. So it seems that naturally shadows of the stress tensor and current, they have conformally soft values. So when we restrict those to exactly plus or minus pi over 2, we are going to get operators in the reduced theory that have the right quantum numbers to give rise to soft operators and to reproduce soft theorems. So that's something that we can, in fact, we can check. And for the case of the stress tensor, we can basically construct its shadow, which is basically this T tilde here. And then from the shadow, we can construct these two operators we call NAB0 and NAB1. And it's easy to see that NAB0 has dimension 1 because the shadow stress tensor has dimension 0, while NAB1 has dimension 0. So they have leading and subleading conformally soft graviton dimensions. These indices here, they are tangent to the sphere in particular. And the claim is that these operators, they are exactly the leading and subleading conformally soft gravitons. That as we insert them on correlation functions, we reproduce the soft theorems. And that turns out to be the case, and it's implied by the stress tensor word identities. So if we start with the stress tensor word identities, we can check that NAB0, when inserted in correlation functions, takes this form. And this is exactly the leading conformally soft factor. So basically, we reproduce the leading conformally soft graviton theorem. And for NAB1, the same is which is basically the subleading conformally soft factor. In particular, the reason why this is exactly the subleading conformally soft factor is because, well, these are the conformal generators, the global conformal generators acting on these operators. But it's possible to show that in this formula here, the indices are restricted in a certain range in which the cylinder conformal transformations, they reduce to the lower dimensional Lorentz transformations acting on conformal primaries. So that's basically, so this takes the form of the subleading soft. So both leading and subleading conformally soft theorems do follow from this dimensional reduction. So let me just summarize. So celestial holography proposes a duality between quantum theories of gravity and asymptotically flat spacetimes and two-dimensional celestial conformal field theories in the celestial sphere of null infinity, with a key aspect being recasting the S matrix as a conformal correlator, or actually an object that shares properties with a conformal correlator, by means of changing the basis of asymptotic states to conformal primaries. It's possible to show that celestial amplitudes, they naturally arise as we take a large AdS radius limit of AdS within diagrams with particular kinematics. And these results suggest that celestial CFT is closely related to dimensional reduction of standard conformal field theories. And in particular, we can show that the symmetries, at least the first few soft symmetries, do emerge from this dimensional reduction procedure as expected. So I will stop here and thank you.
Okay, thank you very much. I enjoyed this talk very much. I think we have now plenty of time again for questions. And I would say we first start maybe with an anonymous question.
Mm-hmm. So we have 3 anonymous questions here. I'm going to read them in order. So the first one is, under which circumstances does the omega-1 plus infinity algebra show up? I guess on tree level or some other highly constrained regimes such as self-dual gravity. What about loop level and quantum deformations?
Okay, The analysis of the
Sorry, your
has
connection
been done.
Your connection
at
failed
three
there for a
levels.
sec. Could you repeat, please?
Can I go? Yeah, right. So yeah, W1 plus infinity has been, the analysis of W1 plus infinity so far has been done at 3 level, and moreover, it focuses just one. Well, there's one important point that I basically glossed over, that when we take these, let me just get back here to the slide. When we take these coincidence limits on the sphere, right, we can take either a holomorphic or an anti-holomorphic limit, and it's important which of them we take, because there are some subtleties related to order of limits issue. And that's also related to, I mean, the helicities of the particles that we are considering. So in this construction of W, basically we start with positive helicity gravitons. So the currents, they are generated by positive helicity soft gravitons. So that's something else. So there are some restrictions, like the analysis has been at 3 level. It considers just half of these currents, because it just considers the positive helicity ones. About corrections, I mean, as far as I know, loop corrections have not been worked out. It turns out that in self-dual gravity, it has been shown that W1 plus infinity is not corrected. So this W1 plus infinity it remains in self-dual gravity, but not focusing on self-dual gravity. As far as I know, there has been no results on loop corrections. And corrections due to effective field theory operators, I mean, recently there was one analysis of one such possible correction to the analog algebra in gauge theory, but it was said that in the paper that a similar story should occur in gravity, and it's probably something that is going to appear at some point. So, but yeah, but well, summarizing, there are several sources of possible corrections to this that still have to be understood better.
Great, thanks. So the second one would be, what is the benefit of using celestial holography instead of AdS CFT? And what is celestial holography, in quotes, better?
Well, it's different because it's not that it's better. Celestial, it's not a choice, right? Because AdS CFT is holography in asymptotically AdS spacetimes, and celestial holography is holography in asymptotically flat spacetimes. AdS CFT is great, and there are several results that have been derived since it began. In particular, it's possible to use AdS CFT to learn more about conformal field theories, for example. But I mean, for several scenarios in the real world, that's not really what we want. So we would like holography in asymptotically flat spacetimes, or holography in asymptotically DS spacetimes. That's another possibility. Asymptotically flat spacetime is just one situation which approximates well many real world scenarios. And so it's different applications. So there's not one that's better than the other. And I mean, they're just for different purposes, different asymptotics of the spacetime.
Okay, the last one is, given a celestial CFT, can we reconstruct the gravitational bulk spacetime?
Yeah, that's a great question. I mean, as far as I know, there have been no discussions of that yet in celestial holography. In AdS CFT, we have, for example, a very well-known procedure for that, which is the HKLL bulk reconstruction, and there are several developments starting from that. But as far as I know, there has been no analog of that in celestial holography. But I agree that it's a very important question, because if it's really, I mean, in holography, we believe that the bulk theory, anything about the bulk theory should be encoded in some way in the boundary theory. So there should be some way to do that. So I mean, I believe it's something that needs to be better understood as well.
Okay, thanks. So before we proceed with the questions from the audience, let me just stop the recording.